Let's have a look at example 1, and we're told that we're asked to predict the products of the anode and the cathode when the solutions are electrolyzed. And our first example is a potassium iodide solution with carbon electrodes. Okay, so this is in solution, and our electrodes are carbon. And you can see in the diagram at the top of page 15, this is actually how we would frequently set this up. And we'll do this prep. You have a retort stand and a clamp onto a U-tube. Because we can't, we have to have them all in the one container, but we're trying to separate it out to see what's happening at each electrode. So the clamp is holding up the U-tube, and then we put our electrodes into the top here, and we're going to connect them up to the power supply as normal. Another part of these questions is that they will ask you to say what you would observe at each electrode. So you might be seeing things like a colour change, or you could also see something if you had an indicator, or you could be seeing bubbles forming, if you're producing a gas. So we need to keep a track of what's occurring at each electrode. Now remember, our process is to list the anode and the cathode, and that the anode has a positive charge and the cathode has a negative charge. And we want to list all of the anions and water that's present. So I have iodide ions present, and I have water present. I also have a carbon electrode, but it's inert, so we're not really. That's not really going to impact on our reaction here. For our cations, we've got potassium ions, and we also have water. And like I said, we have a carbon electrode for the cathode too, but because we reduce onto it, it really doesn't matter too much. We're not going to be oxidizing it. That's when we need to worry about for the anode, but we're not going to be oxidizing the carbon electrode. So we can ignore this one straight away, and that one. And we can ignore this one too, because we know we cannot reduce potassium ions in solution. So now we're left with the iodide ion and the water at the anode. We know the only reaction that will occur at the cathode is reduction of water. So what does the reduction of water look like? That's where we have to go back to our electrochemical series. And remember, if we're reducing the water, we produce what? Hydrogen gas, that's right. But let's have a look at this one for the anode and compare the iodide ion and water. The iodide ion, where is it? It's down here. And which half equation are we comparing it with for water? The top one. Yeah, we don't want to compare the reduction half equation, because we have to compare like with like. So we're comparing the iodide ion with water. And the stronger reducer will oxidize first. So which one? The iodine ion. Okay, so this one is first. If my reaction went on until I had consumed all of the iodide ions, then this one would actually happen second. But one thing that will never happen is that. So once we have worked out which one our stronger oxidizer and our stronger reducer, then we can write out the equations for what's happening at the anode and the cathode. So just our reactions off our electrochemical series. 2I minus. What do you think we might observe at the anode? If this is what we're producing, what are we going to see based on your experiences from previous pracs?
A solid form.
Yeah, what did it look like? Yes? Purple? Yeah, and it could also look what? Sometimes it looks brown. It's quite a dark colour. And then for our cathode, what are we going to see at our cathode?
Hydrogen formed bubbles.
Bubbles. What else could we potentially do? We could add indicator. And what would we see?
Red.
Oh, red. Purple.
Oh, yeah, sorry.
You know, if this is universal indicator. But even if it happened to be phenolphthalein, we'd see pink, wouldn't we? We should be able to figure out how we can identify the hydroxide ions. And we can also work out the minimum voltage that is required. We are looking at the difference now between them on the electrochemical series. We also need to be careful that we are justifying this on the basis of 1 molar solutions. Because if we deviate from that, then the voltages will be different. The voltages are related to the concentration. So if we find this half equation for our anode, what's our value there? Well, it's positive the way it's written, so when it's oxidation we have to change the sign. And then what about our water? And because we are, we add them together, and we're going to get what? 1.37, I think. Yep. That negative there tells me that it's required. Therefore, 1.37 volts required. Okay. Are we ready to look at the next example? Just rub this whole out. So the second example is copper sulfate solution and carbon electrodes. So we have the anode, which is positively charged, and the cathode, it's negatively charged. I have the sulfate ion, and I have the carbon, and I have water. What should go at the cathode? Copper ions and water. Now we know that we can discount these two, which means that the only reaction that can occur at the anode is the oxidation of the water. But for the cathode, we're now going to have to compare strength of oxidizer of water and copper. So we look at our electrochemical series, and where's the Cu2 plus ion? Find it? You see it? Where's the water that we need to find? Down the bottom, here. So the Cu2 plus ion is a significantly stronger oxidizer, isn't it? And so it will reduce first. This one is first. It's a stronger oxidizer than the water. If we ran on and on until we had no copper ions left, then this one would go second. And you don't have to do this at the moment, but there are questions later on where you ask for this sequential oxidation and reduction, and so we may as well talk about it now. We're not doing anything with it, we're just recognising that that could be the case. So the same process. Now we're oxidising our water. So at our anode, we've got 2H2O, it's giving us 4H plus O2 gas. Plus 4 electrons. So what are we going to see at the anode for this reaction? Bubbles. And what else could we observe? Okay, we can add indicator. And what colour will it be? Go red. For our cathode, we're talking about the reduction of the copper. And what do we think we're going to see here? We're told it was carbon electrodes. What are we going to see at the cathode? What colour is copper? It's metal.
Red.
We're going to see a metallic deposit on the cathode.
Yeah, but what colour is that?
It's sort of like a goldy sort of colour. Oh, coppery colour.
Copper.
I don't even have pictures of red colour. It's like golden
You know, gold is sort of a pale colour, whereas copper is a darker colour. But it's got that sort of bronzy sort of tinge to it.
Oh,
Bronzy
where's
sort
the
of.
green?
Okay, now we have to determine the minimum voltage. So we're finding our half equation there for water. What's the voltage? What's the voltage for this one?
-1.23.
-1.23. And what's the voltage for this one?
Like,
So when we add these together, it's actually incorrect in the booklet there. It should say so 0.34 minus 1.23 gives us negative 0.89 volts. So therefore 0.89 volts is required. we getting the hang of what's going on? Yeah. There are quite a few more examples. Same process. So if we just talk about example 3, the sodium sulfate with carbon electrodes is identical to what's happening over here in the Hoffman voltameter. The only difference is that they're platinum electrodes rather than carbon. But we know that we are oxidizing and reducing the water, and that we can observe the oxygen gas and the hydrogen gas at the appropriate electrodes. But the minimum voltage there is quite high, and this is one of the reasons why developing hydrogen as a fuel has been a problem. We have lots of water around. We know that if we split water into its components, that hydrogen is a great fuel, but it requires a lot of energy to get the hydrogen. And so to try and get that trade-off, to try and extract the hydrogen as a fuel without needing a lot of energy input has been a big focus for technology. So let's go on and let's talk more about the one on page 18, which is concentrated sodium chloride. Now, I have said a couple of times that the electrochemical series will only work for 1 molar solutions, or that we can only use the voltages, etc., for 1 molar solutions. And so if we've got a concentrated sodium chloride solution, anytime it says concentrated, that's a clue that the electrochemical series is probably incorrect for that particular reaction. And the question will give you the product. And so if we read this, in this case a student noted that a pungent green gas was given off at the anode. Well, that's not oxygen, is it? No. So that means chlorine gas. And this is the way the question will be presented to you. It will tell you in what way it differs from the electrochemical series. So you do need to be aware that there's an observation that will give you the clue. Again, we've got carbon electrodes. We've got our anode, that is positive, and our cathode, that is negative. And so we've got chloride ions and we've got carbon. We have some water. And if we looked at the electrochemical series, we would think to ourselves, oh well, you know, water is a stronger reducer than the chloride ion, and so under normal concentration conditions, we would expect to oxidize the water in preference to the chloride ions. But in high concentrations, the chloride ions are oxidized in preference. Okay, so this is from observation. We can then just look at our electrochemical series and find that half equation for the oxidation of the chloride ion. And we'll match up then with our production of a pungent green gas. Now for our cathode, all we've got present are sodium ions and water, and so we don't have any choice. It's got to be the water. We're going to be reducing the water. We aren't going to be able to say the voltage required. Why not?
Because we can't use the electrochemical series.
That's exactly right. We can't use the values on here because they are for 1 molar solutions. We already know that it's not applying in this case because we've had to use our observation rather than the electrochemical series, so we cannot say. There's one more condition that we should talk about. So this is for concentrated solutions, but they're still in solution. Okay? Now we're going to look at if they're just molten. This is obviously very high energy. So if we have molten sodium chloride and platinum electrodes, so for the anode, for our molten sodium chloride with platinum electrodes, we have our anode and cathode. What do we put for the anode? What will we list for the anode? Chloride ions. What do we list for the cathode? Sodium ions. We could put the platinum there as well, but we know it's not going to react. We've got time to just finish this off. So for our anode, we have a chloride ion. This time it's liquid because it's molten. And our cathode, this is how we can produce our metals. So we know we couldn't reduce sodium in solution. We can reduce it if it's from a molten ion. But it's very high temperatures, and so these aren't aqueous anymore because there's no water. If it's aqueous, there's water. Okay, they're not solids or gases either, so they're liquids. And because it's very hot, this will also be a liquid when we make it. Does that make sense? We haven't talked about the balancing that we can do, but we'll worry about all of that later on. Okay, so we've knocked over. We have to go through all those examples in one go.